Alright, in this video here we're going to talk about direct variation. So direct variation is something that has this form here, y equals k times x, where k is not equal to 0. Right? And k in this case is what we call a constant of proportionality. Right? So direct variation, basically it's a linear equation, right? It's like in the y equals mx plus b form, but there's no plus b at the end, which basically means that the y-intercept is 0. Right, and that k, that constant of proportionality, is like the slope of the line, right? So most of the times when you do problems that involve direct variation, they're word problems. They have to do with real life situations, and a lot of the things in the sciences involves different types of variation, right? So and direct variation is just one of many types of variation that we'll be talking about in several videos that I have coming up here. So direct variation, when you're doing one of the word problems, the key words that you look for that let you know that it's going to be a direct variation problem, and it's going to be an equation that looks like this, y equals k times x, it'll say varies directly, like y varies directly with x, or y varies directly as x. When you see those words varies directly, well, that's direct variation. Or it might say directly proportional, y is directly proportional to x. Or just y is proportional to x, right? So if you see any of those key words, that's telling you that it's going to be this type of relationship, y equals k times x. All right, and graphically what this looks like, just like I was saying a minute ago, right, it's a linear equation with a y-intercept of 0, right? So if you were to graph the equation for any direct variation problem, it's going to be a straight line that goes through the origin, and the slope of that line is equal to that k, that constant of proportionality. This is what it would look like if k is greater than 0, right? If it's a positive number, right, because this line has a positive slope. If k was a negative number, the graph would be coming down like this and going through the origin that way. All right, so that is what direct variation looks like. I'm going to pause this video here and erase some of this stuff and then put up an example, and we'll work through a problem that involves direct variation. Alright, so I got an example problem up here, which actually took a really long time to write down. Like I said, a lot of these variation problems have to do with sciences and with physics. There's a lot of variation in a lot of the laws of physics and things like that. So a lot of the examples will be ones kind of like this, right? So in this problem, we have the distance a body falls from rest varies directly as the square of the time it falls. If a skydiver falls 64 feet in 2 seconds, how far will he fall in 10 seconds? All right, so first thing, the clue as far as which type of variation that we are dealing with. Right, remember that there are other types of variation. There's direct variation, there's inverse variation, there's joint variation, and I'll be doing videos of all those other ones as well. All right, this video we're just talking about direct variation, so we pretty much know what it's going to be. But if you're just doing a problem and you're not sure what type of variation it's going to be, the words in the problem that tell you that are right here. Right, it varies directly. Alright, that's what's telling us direct variation. That means my equation is going to look like this, y equals k times x. Alright, so that's the first thing with one of these problems, is identifying what type of variation you've got. And again, there are going to be some key words, some clues in the problem that will tell you what it is. Right? If this one says varies directly, we know it's direct variation. If it says varies inversely, well then we know it's going to be the other type, which is inverse variation. Alright, so that's the first thing. We identify that we have direct variation. We have a mental picture of what our equation is going to look like. Now we got to go ahead and solve this problem. If a skydiver falls 64 feet in 2 seconds, how far will he fall in 10 seconds? Alright, so the first step in doing one of these variation problems, after you identify what type of variation you have and what the equation is going to look like, the first thing you have to do is find that constant of proportionality. You have to find that k value. Right? Almost all of these problems that involve the different types of variation, almost all of them are two-step problems. Right? The first thing we have to do is find k, and then we can put the k into the equation and then plug in the other number we have to actually solve the problem that they're asking us to solve. Right? Notice they give us two different things of information here. They tell us that a skydiver falls 64 feet in 2 seconds, and then we want to know how far he falls in 10 seconds. I can't just go ahead and answer that question. Right? I have to use this fact that he falls 64 feet in 2 seconds to help me find the k value, find that constant that I need, and then I can use that to figure out how far he falls in 10 seconds. Right? So again, it's always going to be like a two-step process to do something like this. All right, so first thing I'm going to do here then, when I need to find k, is set up what my equation is going to look like. Right? So we have the distance that the body falls So let me call that d for distance, and then it varies directly as the square of the time that it falls. So let me call the time t. Right, I could use y equals kx as my equation, but my advice when you're doing a problem like this is to use variables, use letters that correspond to the things that they stand for. So instead of y equals k times x, right, the distance, d, varies directly, so equals k times the square of the time it falls. So k times t squared, right? Another important thing here that is real easy to miss, it doesn't just vary directly as the time it falls, as the square of the time it falls, which means it varies directly to t squared, not just t itself. All right? And again, instead of doing y equals x squared, I'm going to write it as d equals k times t squared, because then I know that d means distance and t means time, so when I have to plug numbers in, it's not that hard to figure out where the numbers go. Whereas if you just use y and x every time, sometimes you get confused. Like when I have to plug in my 64 feet in my 2 seconds, I'm going to be like, well, was y the feet or was y the seconds? And which one is x? And I'm kind of confused about which one it is. Here, 64 feet, that's my distance. 2 seconds, that's my time. I know exactly where to put those numbers because I use letters that are appropriate to the problem that I'm working with. All right, so you don't have to do that, but I would strongly advise you to do that. Use letters, use variables to represent what those things mean, just so it's easy to figure out where to plug all the numbers in. Because like I said, with these problems, it's always going to be like a 2-step process. So you're doing a lot of plugging numbers into different places, and it's easy to get confused if your variables don't make sense for the problem. Right? So my distance d varies directly, so d equals k, as the square of the time t. So d equals k times t squared. Right? So direct variation, that constant k is multiplying the other variable, and in this case it's multiplying the square of the time, which means t squared. Right? You could have direct variation where it varies directly as the square root of something, so it would be like k times the square root of t, or it could vary directly as the cube of time, so it would be k times t to the third power. Right, so sometimes you do have to read these problems carefully and look for, is there an exponent or something that I need to put on my variables? In this case, it's the square of the time, so I have to square my time, t squared. All right, so that's what my basic equation is going to look like, and now I need to use that to find what k is, and I have to use this information they give us. He falls 64 feet in 2 seconds. In order to figure out k, I need to know a distance and a time. Right? In order to solve an equation for k here, I need to plug in numbers for all the other variables that I have. Right? So my distance is 64 feet, and again, since I named it d, I know that represents distance, so it's easy to figure out where to put that 64. And I know my t represents time, so it's pretty easy to figure out that I plug that 2 seconds in for the t. Right? So 64 equals k times 2 squared. Right? So once we read the problem, we figure out what type of variation we have, we set up the basics of what our equation is going to look like, then we plug in the numbers for what they give us. 64 feet in 2 seconds, I plug those numbers in for d and t, and now I solve for k. All right, so I have to do 2 squared, which is 4. So 64 equals 4 times k, and then I divide both sides by 4, and that's going to give me that k is equal to 16. Right? So I solve for my constant of proportionality, k is equal to 16. Once I solve for k equals 16, I plug that back into my, my general formula of what this looks like. Right? So I have d equals 16 times t squared. Right? And that was supposed to be an arrow there. Not quite sure what it turned out to be. All right, so my d is equal to 16 times t squared. So that's the first couple steps. Again, identify what type of variation it is, set up the basic formula, make sure you use variables that are appropriate, look for squares or square roots or cubes or things like that, so that if you have to raise these to powers, you're aware of that. Plug in the numbers they give you, 64 feet in 2 seconds, solve for k, rewrite the equation with that k value in there. Now I'm ready to actually answer the question. How far will he fall in 10 seconds? Right? I couldn't just from the very beginning plug in 10 seconds for t because I don't have enough information to figure out what the distance was going to be. I had to figure out what k is first. Now I can plug in t equals 10 seconds. Right? And again, because I named that variable t, it's pretty easy to figure out that the 10 seconds is a length of time, so I plug that in for t, not for the d, which represents a distance. Right? Again, that's the benefit of using letters and variables that make sense. All right, so d is equal to 16t squared. I'm plugging in t equals 10 seconds. So d equals 16 times 10 squared. 10 squared is 100. 100 times 16 is 1600. And my distances here are measured in feet. So d equals 1,600 feet. Right? So if this skydiver falls 64 feet in 10 seconds, or in 2 seconds, then in 10 seconds he's going to fall 1,600 feet. All right, so that's an example of direct variation. These problems can be a little bit tricky, but as long as you identify the type of variation you have, you know what your formula looks like. From there, it's just plugging in the numbers, solving for the constant, and then plugging in the other number you're interested in to get your solution. All right, so that's direct variation. Make sure you check out the other videos I'm going to do with the inverse variation and the joint variation, because those are really similar to this, but the equation you set up is different for those different types of variation. The basic method for solving them, though, you'll see is going to be pretty close to the same, right? So make sure you check out those videos as well.